I'm going to show you how to calculate the entropy change of cooling at constant volume. And the starting point of this is, of course, the first law, which states that the infinitesimal change in entropy is equal to an infinitesimal change in the reversible heat divided by temperature. Let's start with the first law. We know that the change in internal energy is equal to the amount of heat that comes into the system plus the amount of work that is done on the system. If the change is occurring at constant volume, then the amount of expansion work done is 0, because the expansion work, you might remember, is PdV, and if the volume is constant, this term is 0, which means that the change in internal energy is equal to the heat transferred. Now, internal energy is a state function, so we can choose a reversible path, and we can say that a reversible change in the internal energy is equal to the amount of reversible heat that comes into the system. And based on the previous discussion, we can write the internal energy as the product of the number of moles multiplied by the heat capacity at constant volume multiplied by differential change in the temperature. Then we plug in these values there. So we can write that the change in entropy is equal to the reversible heat, which is equal to the change in internal energy divided by the temperature. And now we can integrate this to find the total change in entropy when a system is cooled at constant volume. So we integrate from the initial temperature to the final temperature. N and the molar heat capacity are constants, so they come out of the integral, and you are left with dt by T, and this is equal to the number of moles multiplied by the molar heat capacity multiplied by logarithm of T2 by T1. So this is the total change in entropy of the system when a system is cooled. Now remember that if the system is being cooled, then T2 is smaller than T1, which means that this number is negative and the change in entropy of the system is negative. But this doesn't violate the second law, because the entropy of the surroundings will increase at the same time.